Hello, my name is Zhang, a PhD student from Iowa State University. The paper I present today is Benchmarking for Observability, the case of diagnosing storage failures. My presentation is divided into 5 parts. Let's begin with the background and motivation. The storage stack in OS kernel is very complex, and it may contain various specs, such as data races and so on. Moreover, the system is being optimized aggressively for NVM, which may introduce new bugs. Bugs may result in various failures that are difficult to diagnose. One example is a Golia incident, which lead to server crashes and file corruptions. After weeks of diagnosis, developers mistakenly blamed Samsung SSDs for the failure. But 1 month later, Samsung's engineers found that the root cause is a Linux kernel bug. Obviously, the existing diagnosis method is not good enough, and more advanced debugging support is needed. Currently, there are mainly 3 types of debugging tools for failure diagnosis. The first one is interactive debugger, such as GDB or KDB. These debuggers can support fine-grained manual inspection. Developers can set breakpoints and manually check information, such as variable values. The second type is tracer. Tracers can collect various events from a running system automatically. For example, ftrace is a software tracer to trace kernel functions, and there are hardware tracers for analyzing storage device commands. Both of them are helpful for failure diagnosis. The third type is record and replay platform, such as TTVM and Panda. These tools leverage virtual machine to record program execution and replay segments of the past execution. They often support plugins to perform additional analysis. While there are many existing tools, we find that there's little measurement of their limitations for debugging. Existing efforts simply measure tools' runtime overhead, which cannot show how effective the tools are for diagnosing the root cause of failures. Therefore, more benchmarking efforts is needed. So what should we measure? We found that the concept of observability proposed recently is very relevant. It basically means the observation that debugging tools allow the developers to make, which contains 3 properties: versatility, repeatability, and expressibility. Unfortunately, there's no concrete metrics for measuring the important observability, and this work is the first step toward addressing this challenge. Then I will move on to the second part, understanding real-world storage failures. While there are many anecdotes about failures, there is little quantitative understanding of their characteristics, so we perform a study on real-world failure first. We collect storage failure incidents reported on kernel Bugzilla. We use keyword search such as corruption, data loss, and so on, and focus on storage-related components such as file systems. For each report, we collect and calculate 7 types of info such as time of duration and number of participants. The figure here shows an example report which we used to drive the information. We studied 277 incidents in total and summarized them in this table. The result means the incident has been resolved. We can see that the incident took multiple months to resolve on average, which required multiple rounds of discussions and multiple participants, and more than half of the incidents in our data set haven't been resolved yet. Such data shows the difficulty of diagnosing storage failures quantitatively. Next, we found that the incidents involve all major storage components, and the file system and drivers tend to include more bugs. The result is consistent with previous studies and implies that debugging tools need to provide full-stack observability. Third, the average debugging time is constantly long across all components, which implies that better debugging support is needed for all components. Fourth, among all resolved incidents, 37 cases involve multiple OS distributions or kernel versions. This implies bugs may elude intensive testing and snag into new releases. Thus, testing in the development environment is not enough, and debugging support for failure diagnosis is always needed in practice. Last but not least, only 5 resolved issues were caused by hardware, which implies software bugs remain dominant for causing storage failures, and observing the behavior of the storage software is important. Next, we will introduce the bug bench K derived from the study. The backbench case collection of realistic reproducible service failure cases. For each case, we collect all necessary information for reproducing, including bug triggering codes, environmental information such as OS distribution, kernel version, and system configuration. The right-hand side figure shows an example. We packaged all necessary information as virtual machine images, which enables realistic benchmarking and measurements of debugging tools. The current prototype of BugBenchK contains 9 cases covering 4 different file systems and the block I/O layer. The table summarizes the 9 cases. The critical function column shows the buggy kernel function there are identified as a root cause of the failure, which are related to semantic or memory issues. They require different number of lines of patch to fix, and we created the workload in C, Bash, or a combination of both to trigger them. Next, we will use BugBenchK to measure the debugging tools. We evaluate 2 representative debugging tools, ftrace and Panda. The former one is a tracer built into the Linux kernel. The latter one is a VM-based recode and replay platform for program analysis. Overall, we have measured a concrete set of metrics showing their observability based on their features and identified limitations in both. We also enhanced the observability of both tools by adding command-level information in our extension experiment. For ftrace, we measure its key feature, kernel function tracing. Specifically, we consider if a bug case can still be reproduced when traced by ftrace, calculate the total number of functions, unique functions, and critical function traced by ftrace. If there's no any critical function observed, we will further calculate the shortest distance, which is defined by the minimum number of function invocations needed for the traced functions to the missing critical functions. Let's see the result. First, we found all cases still can be reproducible. This means ftrace is non-intrusive for failure diagnosis, which is important. Second, we found the ftrace provides rich function-level information ranging from 6,000 to more than 100 million functions in total. Although the number of unique functions is much fewer in all cases, this implies that buggy functions may be invoked many times in causing the failures. More interestingly, ftrace cannot capture all critical functions that cause the failures. This is because ftrace relies on a predefined list stored in available filter function file in debug.ms for identifying traceable functions. For case 2 and 4, although the ftrace cannot capture any critical functions, they can capture closely related functions, which is still helpful for debugging. For case 6 and 7, ftrace cannot generate any traces and thus provides zero observability, because both failures manifest as kernel panics, which affect the internal ftrace. This implies that built-in tracers like ftrace is fundamentally limited for diagnosing severe storage failures. Finally, we noticed that case 9 contains a lot of traced functions. The substantial number of traced functions may dilute the debugging focus. Thus, more intelligent method is still needed to automatically reason the root cause. Our second target is Panda. As mentioned earlier, Panda is a recode and replay platform, and it supports different plugins which can provide different types of observability, such as CPU instructions, process IDs, and so on. So, we measure whether the key features can work properly and provide the expected information for diagnosing BugBenchK. First, we found that 8 out of the 9 cases can still be reproducible with Panda, and all features work properly in these cases. Even for the 2 kernel panic cases that ftrace cannot handle, Panda can still work and provide the expected information. This is because Panda leverages a virtual machine to achieve isolation. In other words, isolating the target storage software stack from the tool itself is important. On the other hand, Panda cannot provide any observability for the last case. We found that this is because the case generates many non-determinism events in the kernel, which overwhelms Panda's full-stack recording component. The results suggest that reducing the overhead of VM-based full-stack tool is critically important. Through the experiments with ftrace and Panda, we found that neither tools can provide complete full-stack observability. In particular, they miss the communication between the OS kernel and the storage device. Such low-level information is usually captured through special hardware. So, we further explore how to extend both tools with a low-level observability without hardware support. For F-trace, we leverage a customized SCSI driver to intercept device commands while tracing the kernel functions. Then we stitch the function level trace and the command level information through timestamps to extend the tool's observability. The figure shows an example of the extended trace. Please refer to our paper to see how the command level information may help diagnose the root cause. Similarly, we intercept the device commands through a customized QEMU and recode them together with instructions. The right-hand side figure shows parts of the extended log, which enhance the tool's observability too. In this way, we achieved low-level observability without relying on special hardware. Finally, I will conclude the talk with future work. We have derived the BuckBench from real-world storage failures, which enable realistic benchmarking of debugging tools. Through our experiments, we found that building-in tracers relying on the kernel may be fundamentally limited, because cannot provide any observability when the kernel is severely affected by failures. VM-based tools may be more viable due to isolation, but heavy overhead can make a failure unreproducible. Also, both types of tools may generate substantial information, which still need much more human efforts, and both methods may miss the low-level information, which may be remedied by lightweight extension. Based on our study, it's clear that less intrusive and more intelligent solutions are needed for enhancing the debugging observability, and we believe that more benchmarking efforts can guide the design of new solutions. In the future, we will add more cases to BuckBench and derive more metrics and evaluate more tools. Also, we will try to build intelligent debugging tools to reduce debugging efforts. This is the end of my presentation. Thank you.